everyone, now we are going to solve problems of first-order differential equations. Now let's start with the first problem. Here is the equation, x dy plus 3y dx is equal to xy dy. By writing this equation in the form x minus xy dy plus 3y dx equal to 0, we recognize that this equation is not exact because the derivative of n with respect to y is 3 and the derivative of n with respect to x is equal to 1 minus y, which is not equal. However, we can make this equation an exact differential equation by multiplying an integrating factor. In this equation, our integrating factor is 1 over xy. Now we multiply this equation into 1 over xy. So x dy plus 3y dx equal to xy dy times 1 over xy. We have dy over y plus 3 over x dx equal to dy. So become dy minus y minus dy plus 3 over x dx equal to 0. And this dy over, we can simplify this dy over y minus dy to become 1 over y minus 1 dy plus 3 over x dx equal to 0. Now we can see that this equation now is now exact because m of y is equal to 0 and also the n with respect to x. Now we can integrate the equation. Integrating dy over y plus 3 over x dx equal to dy, we get ln y plus 3 ln x equal to y plus c. Now simplify this 3 ln x will become ln x cubed and y plus c. You can simplify further. Now the final answer is ln of x cubed y is equal to y plus c. This is the general solution of our equation x dy plus 3y dx is equal to xy dy. Next problem is we'll determine if this function is homogeneous or not. We will test its homogeneity by letting x is equal to xt and y is equal to yt. If the function of xt and yt is equal to e raised to n times f times the function of x and y, then it is said to be homogeneous. So we now have f of xt. We now substitute the value of xt, of the value of x and y. So we have now sine of xt over xt squared plus yt quantity squared. So we now have sine of xt over x squared e squared plus y squared e squared. Now then we have sine of xt over e squared times x squared plus y squared. Now simplifying, we have x over t times x squared plus y squared. Now we can see that this equation is not equal to the function of xt and yt is not equal to the function of x times y times the t raised to 2 squared. So this function is not homogeneous. Our next problem is finding a general solution for this second equation y prime is equal to xy squared plus the quantity of 1 minus 2x times y plus x minus 1, which if u is equal to 1. One solution of the rectangular equation y prime is equal to p of xy squared plus q of xy plus r of x is known as y is equal to u of x. By substitution of y is equal to u plus 1 over z, the equation can be transformed to a linear first-order equation with new dependent variable z. This linear first-order equation is z prime is equal to negative times the quantity of p of x times 2u plus q of x times z minus p of x. So first, we find what is our p of x and q of x in our equation. Our p of x is equal to x, and our q of x is equal to 1 minus 2x, and our r of x is equal to x minus 1. Applying linear first order equation, transformation of Riccati gives z prime is equal to negative. The rp of x is x, then r times 2u. Our u is equal to 1, so this is 1, plus our q of x, which is 1 minus 2x, times z minus p of x, which is equal to x. So we now have c prime is equal to negative of 2x plus 1 minus 2x times z minus x. We'll cancel 2x, so we have 1 z minus x. Z prime is equal to negative z minus x. Z prime is the same with dz over dx is equal to negative z minus x. So we have dz over dx plus x is equal to, plus z is equal to negative x. You can see now that this is a linear equation. So we have dz again, dz over dx plus z is equal to negative x. We will now find its integrating factor. Our integrating factor is equal to v is equal to e raised to the antiderivative of 1 dx, which is equal to e raised to x. Multiply this integrating factor to this equation. We now have v over dx times our dependent variable, which is z, times the integrating factor dx is equal to negative x times our integrating factor e raised to x. So we will now integrate this. So integrate, we'll have z e raised to x is equal to negative x negative x times e raised to x plus dx. So we have negative x e raised to x plus e raised to x plus c. Dividing both sides by e raised to x, we have z is equal to negative x plus 1 plus c times e raised to negative x. We now substitute this into this equation, y is equal to u plus 1 over c. So now we have, therefore, y is equal to, ru is equal to 1. So 1 plus 1 over rz is equal to negative x plus 1 plus c times e raised to negative x. Then simplify, we have y is equal to negative x plus 1 plus c e raised to negative x times negative x plus, we have here, plus 1. So this will be over equal to negative x plus 2 plus c e raised to negative x over negative x plus 1 plus c e raised to negative x. So this is now our final answer. This is the general solution of our equation. Next problem, we are going to find the general solution of this equation x e raised to x squared plus y dx equal to y dy. By manipulating this equation, we can find if what type of differential equation is this. So remember that this equation ex squared plus y is, we can still expand this into e raised to x squared times e raised to y. So this equation will now become x squared plus y dx equal to y dy. It will now become x squared e raised to x squared times e raised to y dx equal to y dy. Dividing both sides by e raised to y, we have now x e raised to x squared dx equal to y over e raised to y dy. This equation will now become x e raised to x squared equal to y e negative y dy. So we can see now that this equation is a separable differential equation. So we may now integrate both sides. We have x e squared dx is equal to y e negative y dy. Integrate both sides. I will first integrate the left side. So I will let u is equal to x squared. I will have du is equal to 2x dx and it will become 1 half du equal to x dx. On the right side, I will let m is equal to y. So dm is equal to dy. And I will let dn into e negative y dy. And so n is equal to negative of e raised to negative y. So in this left side, I will have now 1 half times the antiderivative of eu du, and in the right side, it will, using integration by parts, we have uv minus v du, and in my equation we have mn minus mdu. So negative y e negative y plus the antiderivative of e raised to negative y dy. So we have now 1 half eu is equal to negative y e raised to negative y plus e raised to negative y. So we have now 1 half e raised to x squared. Let u is equal to x squared, so I will now substitute. So it is equal to 1 half e raised to x squared is equal to negative y e negative y. I'm sorry, this is minus. So negative y e raised to negative y minus e negative y. So it will now become 1 half e raised to x squared is equal to e raised to negative y times negative y minus 1. Simplifying, we have e x squared is equal to 2e raised to negative y times negative y minus 1. We now have our general solution of the equation x e raised to x squared plus y dx equal to y dy. Our next problem is for the application of the first order differential equation. So we have the problem, a body of weight W falls from rest under the influence of gravity and a retarding force proportional to the nth power of velocity. Show that the velocity of the body approaches the limiting value v is equal to nth root of W over k. Under some circumstances, a falling body of weight W encounters air resistance proportional to its instantaneous velocity v of t. We use Newton's second law to find the differential equation for the velocity of the body at any time. Assuming that the downward direction is positive, the sum of the forces acting on the body is mj minus kv, where k is a proportionality constant and the minus sign indicates that the resistance acts in a direction opposite to the motion. Newton's second law can be written as ma is equal to mdv over dt, which is a is the acceleration. Equating these two equations gives mdv over dt is equal to mg minus kv raised to n. Remember that w is equal to mg. So this equation will now become w over g times dv over dt is equal to w minus kv raised to n. So we will now divide both sides by w over g. So this equation will now become dv over dt is equal to g minus kv raised to n times g over w. Transforming this into this other side, dv over dt plus kv raised to n g over w is equal to g. We can now see that this equation is an exact differential equation. So we can now solve its integrating factor. The integrating factor is equal to e raised to the antiderivative of kg over w dt, which is equal to e raised to kjt over w. So we will now multiply this integrating factor to this equation. So we now have dv over dt times e kjt over w plus kv raised to n g over w times e raised to kjt over w is equal to g times the integrating factor, which is e raised to kjt over w. This equation is also equal to d over dt times the integrating factor times the dependent variable. Our dependent variable here is d raised to n times the integrating factor, which is e raised to kjt over w. So we will now integrate this. So this will now become dn times e raised to kjt over w is equal to the antiderivative of g e raised to kjt over w dt. So integrating kjt over w will give, integrating this will give g times w over kg times e raised to kjt over w. This will the g will be cancelled. So bn times e raised to kjt over w is equal to w over k times e raised to kjt over, we have plus c here, over w plus c. So we'll now divide both sides by the integrating factor. So we have b raised to n is equal to w over k plus c times e raised to negative kjt over w. Subject to v of 0 is equal to 0, we have 0 is equal to w over k plus c e raised to this equation, the e raised to negative kjt over w will become to e raised to 0. So we have 0 is equal to W over K plus this e raised to 0 is equal to 1, so it should become only to C. So we now have the body of C. C is equal to negative W over K. So we now substitute this, the body of C, to this equation. So we now have B raised to N is equal to W over K plus, minus W over K times E raised to negative KJE over W. Simplifying, we have W over K times 1 minus E raised to negative KJE over W. So we now determine the limiting velocity of the wave. So we can determine the limiting velocity as if we let the t be equal to infinity. So as t approaches infinity, we have v raised to n is equal to w over k times 1 minus e raised to negative infinity. Then e raised to negative will just be equal to 0. So we have Vn is equal to w over k times 1. So Vn is equal to w over k. We now have v is equal to the nth root of w over k. This is now the limiting velocity of the wave.